section at the fixed end. Why am I looking at the fixed end? Is because it contains the point A. My y-axis, x-axis and z-axis are as I have drawn right there. So the x-axis is coming towards you. Y-axis is vertical. And the z-axis is pointing to my left. X-axis coming out of the board. I mark my point of interest, which is the point A. Okay, then I start marking all the forces. From force balance, I figured out that Nx is minus 300 newtons. I had assumed it to be along the positive x-axis, so I have a force which is pushing into the page. So Nx is negative, or it is positive 300 newtons pushing into the page. Likewise, I have Vy and Vz. Vy was minus 200, so I'm going to have a force pointing in the negative y direction. Okay, so this is Vy, which is now plus 200 newtons. Is this making sense to everybody? If I had a force that was negative, when I drew it in the free body diagram, I flip its direction and write it as a positive force. Okay? Then I have Vz, which was also negative for us, I believe, minus 400, so it's pointing along the negative z-axis as positive 400. Then I have all my couple moments. Now I have the torque, first of all, Tx was positive 200 Newton meters, so it's a counterclockwise torque. Then I had mz 400 Newton meters along the positive z direction. And then my was minus 1100 Newton meters, or 110 Newton meters along the positive negative y. Okay, so I'm going to be drawing it somewhere down here. Does my figure make sense to everyone? Yes.
In this case, where is the neutral axis?
It depends on which component of the force you're talking about. If I'm talking about, as we said in the last class, if I'm looking at a bending moment, the bending axis is a neutral axis for this bending moment. If I'm looking at a shear force, for example here, the neutral axis is the axis that is perpendicular to that shear force. If I'm looking at this shear force, what is the neutral axis? It is the axis which is perpendicular to that shear force. If I'm looking at this bending moment, what is the neutral axis? It is the axis of the bending. Okay? Now I'm going to start writing all the stresses at the point A. So this is typically how I do these problems. You can either list everything down step by step. Yes, question.
Why wouldn't the z-axis, the moments from the z, be negative?
Why are they negative?
Yeah,
I did not get them to be negative here, right? So why should I be drawing them as negative there?
I guess because I was looking at, like, it's drawn the opposite direction.
So it is drawn this way, right? So the fingers of my right hand are curling into this arrow. You see, my thumb is pointing along the positive z direction. Okay, so if you want, you can think of it this way. Does this make sense?
Yeah, that makes sense. I'm trying to. Okay.
Yes.
Like on that picture, you had mz equals negative 200 times 2, and you wrote mz equals 400 Newton meters.
That's all right.
Yeah, the other side. It's MC minus 200.
Oh, okay.
What's wrong? Nothing's wrong. No. Is everybody okay with everything? Okay. All right. You guys have a question? Okay. Let me start by calculating the normal stresses at the point A due to the normal force. Okay, so sigma A due to Nx, what is this going to be? This is going to be in the x direction, right? Because obviously it is acting in the x-axis, but it's a compressive stress. So the subscript is going to be xx. The second subscript is the area normal. The first subscript is the direction of the normal force itself. In this case, the direction of the normal force is along the x-axis. And so this is going to be Nx by area. This is compressive. Nx we have obtained it to be 300 newtons. So this is 300 divided by the area. Okay, so this is pi times r square. So 20 by 1000 whole square. And this value I had obtained it as the following. It's around 1800 kilopascals. Okay, so if you see decimals, it is okay to round it out because you always have this factor of safety. There are so many factors of safety layered on into every bit of calculation in mechanics. And this is compressive. Then I start looking at these normal stresses at the point A due to the other forces and moments. Sigma at A. Let's start by looking at the normal stress due to the bending moment mz. If there was one, it should be along the x direction only because of the fact that the area normal is the x-axis. But in this particular case, as we decided many times, as we have written many times, if I have a point on the neutral axis, so for this moment mz, the z-axis is the neutral axis. If I have a point on a neutral axis for a bending moment, the bending stress at that particular point is 0. I look at the bending stress or the normal stress at the point A due to the bending moment my. So sigma A due to my. Once again, what are the subscripts? The second subscript is the area normal. The first subscript is actually the direction of the normal stress, but if you know the area normal, the normal stress will have to follow the same direction for bending stresses or average normal stresses. You cannot have a sigma A xy. That is meaningless. If I look at the bending moment my, the neutral axis is the y-axis. If I go through the calculations, then I end up getting the following. My times y by I about the neutral axis, which is I. You see that I am not putting the positive or the negative sign because we are going to decide on the direction of the bending stress looking at the cross section. Okay, so if you want, you can say this is a magnitude quantity. The directionality comes from looking at the physical cross section itself. If I look at the physical cross section, as I am looking at this moment acting, it is as if my palm is the cross section. There is a line that is slicing my palm vertically into two halves, and then that line is trying to rotate my palm in the following manner. So all the points which are on this side of my palm, which is on the right side of my palm, they are being pulled, and all the points on the left side are being pushed. So these are all tensile, and these are all compressive, which means that the bending stress at the point A is compressive. Does this make sense to everybody? Okay, so bending stress at A is compressive. One can do the calculation, substitute for my. So that's going to be 1100. Y is distance from the neutral axis to the point A. So this is going to be the the radius itself, so 20 by 1000, and pi by 4, r square. Pi by 4 r to the power 4, I'm sorry. That is the moment of inertia for a circular cross section. And this value is going to give you 175 megapascals. This is in compression, okay? The normal stress at the point A due to the normal force was compressive. Look at the magnitude. This is 1800 kilopascals. This is 175 megapascals. This is like a few orders of magnitude larger than that. Which in some sense tells you that, okay, this is inconsequential if I look at failure theories. Nobody cares about normal forces. They don't do much for us. The culprit that breaks things is bending moments. Everything breaks because of bending. Okay? And starting from the human condition, right? I mean, as you grow old, you're climbing the stairs, your body is subjected to all kinds of bending moments as you're climbing. And then if there is a fall, it becomes fatal because of the fact that the bones are bent, and it's the bending stresses that break a bone in some sense. The combination of the bending stresses and the shear forces in reality, but the bending moments are more or less the major culprits. As you grow old, your bones also start deteriorating, right? So there's going to be some porosity included there. There will be certain sections that are weaker than other sections, and so the stresses are going to start playing havoc on those parts. All right, the net normal stress at the point A is now going to be the sum of these two. So it's going to be compressive there, so the total one is compressive. So sigma A, I'm just going to sneak it in here. Xx is going to be 1800 kilopascals compressive plus 175 megapascals compressive, the byline being that the normal stress at the point A is compressive. The net is compressive. Okay. Now we're going to start looking at the shear stresses, and then we'll draw the volume element. Here is my point A. I start looking at the contributions to shear stress. The first contribution is going to come from the torque. Okay, so torsion always causes a shear stress. And which is why if you look at the nomenclature of all these reaction moments, I mean, torsion also comes from a reaction moment. Bending moments are also reaction moments. Why do we call one differently from the other? Is because the effect created is different. Bending moments cause bending stresses. A torsional moment causes a torque, which is a shear stress contributor. Okay? This is the y-axis. This is the x-axis. This is the torque Tx. And it is quite obvious to see that the shear stress due to the torque Tx is going to be acting at the point A in the vertically downward direction. Okay, so now at A, due to Tx, I'm going to write the subscripts. Please look at me here. The second subscript is the area normal to the cross section, so that is the x-axis. The first subscript is the direction of the shear stress, or the torque causing the shear stress is going to be in the y direction. This number by itself does not tell you whether the shear stress is up or down. For that you have to refer back to the figure here, which is why in these cases it is important to show me the figure. Okay, so this is going to be in the downward direction, so this is Tx C by J. Tx was, how much was that? 200 Newton meters. 200. C is the radius, maximum outermost circumference, by J, which is pi by 2 r to the power 4. crunch these numbers in a minute. So this is going to be pointing down. Then I look at the two shear forces, Vy and Vz. I'm going to have Vy, as you can see, E is pointing vertically down, so that's 200 newtons. Point A is sitting right there. So tau A, Vy. This is also going to be having the same subscript, which is the Yx subscript, x being the area normal, y being the direction of the shear force, which causes the shear stress. So this is going to be Yx. We have our formula. Vy, Q. Now, if I have a shear force Vy, the neutral axis is the axis on the cross section, which is perpendicular to the shear force. So for me here, neutral axis is the z axis. So this is going to be Izz times T suffix tau. We have looked at the calculation of Q and so on, so if I draw the figure out here, I can either look at all the area onto the top of A or the bottom of A, so I can look at the area on the top here. This is A prime being pi by 2 r square. And then y bar prime is the distance from the neutral axis all the way to the centroid of this semicircle, which is 4r by 3 pi. We know the value of r. You can do the substitutions. Please do the substitutions. Izz is pi by 4, r to the power 4. And I'll write that out here. And these are the values. So due to the shear force, it's going to be 212 kilopascals approximately. Okay, and then this is going to be in the downward direction. And due to the torque, it is also going to be in the downward direction, but it's going to be a little order of magnitude higher. It's around 15.9 megapascals. So tau A in the Yx direction, the net one is tau A due to Tx plus tau A due to Vy. Both of them being down. Vz is not going to contribute to any shear stresses at the point A because the point A is on the outside of the cross section if I look at the force Vz. Okay? So tau A Vz is 0, since Q is in this particular case. Both of them will be pointing vertically down. This is down. This is also vertically down. And plug in the numbers. I'll be posting the solution of this, my own written solution for this problem, with all the numbers shown. Okay. I'll be doing that for the problems I'll be solving on top of the board pictures. State of stress. You can either draw the cross section or you can work with the cross section that you already have. Okay, so if I look at it here, bear with me for a few more minutes. The shear stress, the net shear stress is going to be acting vertically down. Okay, so this is vertically down, the net shear stress. The first arrow that is drawn is that. And then if you look at the compressive stresses, they are acting into the plane of the cross section. Sigma A stresses are compressive. So I'm going to have something pushing into the cross section. Okay, so this is tau A Yx, sigma A Xx. Take that volume area element, draw it as a volume element. On the face that I see, shear stress pointing vertically down, which means on the back face, equal and opposite. On the top and the bottom faces, I'm going to have a couple moment, cancelling the effect of this rotation. Normal stresses on both faces. Back face. And sigma A, XX, A, YX. Shear stresses are symmetric, so if I write out the stress matrix for the point A, I will not have any other things besides sigma A and tau A XY. Sigma A XX, tau A XY or YX, and these are all the stresses that are present at that particular point. Everything else is going to be zero. There are no normal forces or normal stresses or bending stresses in the Y and the Z at the point A. There are no shear stresses in the Z direction for the point A. Plug in the numbers and this will be the stress matrix. Okay, thank you.